Hello, my name is Kyle Eichmeyer and I'll be talking to you today about the applications of graphene. First, I will start with what graphene is. Graphene is a carbon allotrope, a single, thin, 2D layer of graphite. It comes in a hexagonal honeycomb pattern of atoms, basically just very small atomic chicken wire. It is one of the best electrical and thermal conductors in today's world, and many layers of stacked graphene will create graphite. This is shown in the image to the right, with a single layer of graphene on the right of the image and then graphite on the left. Graphene has very many interesting properties. To start, it has a tensile strength of about 130 gigapascals, which depending on the type of steel you're looking at can be between 100 to 300 times stronger. It has a Young's modulus of 1 terapascal, which is equivalent to about 150 million psi. Graphene is also very flexible and also transparent. This can be seen in the image to the right of a technician who has produced a layer of graphene and is bending it, and you can also see through it. Graphene has a thermal conductivity of about 5,000 watts per meter Kelvin at room temperature, compared to copper, which is one of the most commonly used materials for thermal applications. Copper only has about a 394 watts per meter Kelvin. It also has a very low electrical resistance of 3.1 microohms per centimeter cubed. This is even more astonishing when you think that graphene is also only a single layer of atoms. Graphene has been known in the science community for many years now. However, it was mostly only theoretical until 2004 when Andrei, Jim, and Konstantin Novoselov produced the first physical specimen of graphene at the University of Manchester. They did so while working on another project. They used Scotch tape to try and shape a graphite sample they were working on, and then noticed the small flakes of graphene that were being removed. Through this process, they were able to win a Nobel Prize in 2010 for physics. The images below, on the left, shows the process of taking graphene off of a graphite sample using an adhesive strip. A physical, real example of this is shown to the right. The most common process to manufacture graphene is through chemical vapor deposition, or CVD. In this process, shown in the image on the right, graphene is produced onto thin sheets of metal, most commonly copper. Through this process, you pump gas into a chamber with a specific set of temperature and pressure, which then causes the graphene to first start seeding onto the metal sheet and then continually form into a sheet of graphene. After the graphene is formed on the metal, it then has to go through multiple steps of removing the graphene from the metal sheet so that it can be used in multiple applications. This process has many downsides though. It does have some toxic chemicals that have to be used in the gases. It is an expensive and long process, especially the after steps of the forming. And it also is fairly difficult to remove the graphene from the metallic layers. The newest development in the graphene manufacturing process, it comes out of MIT in the roll-to-roll process. Essentially, this is the same CVD process as before, except for the copper sheet starts on one roll on one end of the machine and then is robotically sent through the machine at a specific feed rate to produce the desired size of graphene pores. On the exit, it is then re-rolled onto a new roll to be then taken and the graphene removed from the metal sheets. With this process, it allows manufacturers to produce much higher quantities and qualities of graphene. The applications of graphene that I will be discussing today are in flexible electronics, solar cells, water filtration, and batteries/supercapacitors. The idea of flexible electronics has gained a lot of movement over the last few years, and graphene is able to make this happen. The idea of foldable devices is quite popular, as seen in Samsung's foldable phone attempt. Also, a new development is a fitness patch, shown in the image here on the left. It is supposed to be able to do everything your Fitbit can do with a simple patch that you wear on your skin. Other applications include UV tracking patches that detect how much UV light you've been exposed to, and also shoes and insoles that do pressure detection for athletic applications and also have the ability to dissipate heat. Solar cells is another area where graphene has drawn a lot of interest. Because graphene is both highly conductive and also transparent, it is a very sought-after material to be used in solar cells. Graphene has the ability to release multiple electrons per photon hitting it, as opposed to silicon, which only releases one electron per photon hitting it. This allows for improved overall solar cell efficiency, and it also allows for collection of electrons without blocking the sun rays, due to, again, its transparent nature. Research is also being done to allow solar panels to collect charges while it rains. This will be explained in a short video on the next slide.
Finally, let's now examine another use of graphene in solar cells as a charge collector. The third main area of research for graphene in PV is its use as a charge-holding parallel plate, just like in a capacitor. Scientists from Ocean University of China have been working on harnessing the power of rain through solar panels. As we all understand that rainwater is not pure and it has positively charged ions of sodium, calcium, and ammonium. A layer of graphene is placed on the top of the solar cell not as a current collector but as an ion holder and a separator. The solar panel is sandwiched between the layer of graphene at the top and ITO and plastic at the bottom. What happens is that the positively charged ions bind to the ultra-thin layer of graphene, forming a double layer, technically referred to as a pseudocapacitor, with the electrons already present. The potential energy difference between the two layers is strong enough to generate an electric current. So far, the energy conversion efficiency has reached 6.3%, but it is the ability to generate electricity come rain or shine that is the exciting prospect of this technology. In other words, we can now create an all-weather solar panel courtesy of graphene.
A third application of graphene is in water filtration and specifically desalination. Desalination is the removal of salt from water. Desalination is done in a process known as reverse osmosis, shown to the image here on the right. It is the process of osmosis just run in reverse, with an applied pressure forcing the water through a semi-permeable membrane that blocks the salt ions from traveling with the water, so that you get pure water on the other side. When graphene is applied to this process as the semi-permeable membrane, it will allow for them to reduce energy costs because they will not have to have as high of pressure, and also there will be lower friction losses through the membrane, allowing water to be pushed through at a higher rate. For this to be done, small pores have to be cut into the graphene sheet of about 0.8 to 1.6 nanometers in diameter. This is done during the production process. Currently, there are problems with the manufacturing process for the semi-permeable membrane. They are having quality control issues producing the needed pore diameter in the graphene sheet. Right now, they are either making it too big or too small, either allowing salt ions through or not allowing enough water through the membrane. But with the new roll-to-roll manufacturing process, this issue may be alleviated. The last application for graphene that I'll be discussing today is that in batteries and supercapacitors. Some applications are laser-described graphene capacitors, or LCGs. These are highly flexible and much lighter than traditional batteries. They have very fast charging abilities, potentially seconds for smaller devices. They have high power densities comparable to that of high-power lithium-ion batteries. There will be a potential capacity increase by a factor of 10 when graphene is implemented into the current batteries/supercapacitors already on the market. Graphene will also have the ability to produce much lighter batteries and supercapacitors than is what currently already on the market. especially when compared to the traditional lead-acid battery. Along with the many promises graphene has in today's world, there's also some drawbacks. The main two being that it is quite difficult to manufacture on a large scale and is also quite expensive to create. As we still learn about this material though, we will hopefully learn new manufacturing techniques to produce them on a large scale and also produce them at a better cost.